Hello, I'm James Clinton, a rising senior engineering major at Harvey Mudd College. This summer, I worked under the guidance of Isha and Professor Zeynep Tamel in the Robotics Institute Summer Scholars Program. My work focused on enhancing heterogeneous swarm locomotion through simple one-degree of freedom arm mechanisms. Swarms of organisms are often found in nature, particularly in insects, where ants work together to form bridges to optimize foraging routes. This strategy of collaborative swarms can also be seen in robotics, with swarms being used to enhance the capabilities of a single robot. In particular, heterogeneity, when a swarm uses different types of robots with different functions, has been shown to increase capabilities and performance of a swarm. Our work builds off of PuzzleBots, an existing reconfigurable robot swarm. It uses physical coupling, a strategy common in modular robotics, to enhance locomotion capabilities. Its coupling is passive, which helps it avoid some of the power consumption drawbacks of typical modular robot coupling mechanisms. It also has two coupling modes, a rigid mode and a flexible mode, which allow for a wider range of capabilities. We aim to fully leverage this passive coupling by building a heterogeneous swarm with mechanisms that enhance 3D locomotion capabilities. Our goals are to increase swarm capabilities by increasing heterogeneity and adding new mechanisms to the swarm. We want to add 3D locomotion capabilities, particularly the ability to ascend and descend obstacles. Finally, we hope to fully leverage the passive coupling in the PuzzleBots, allowing for full range of motion and locomotion capabilities while maintaining the power savings brought on by passive coupling. Our mechanisms are simple one-degree of freedom arms that mount to the front of PuzzleBots. They take advantage of the flexible coupling to allow for unique locomotion capabilities. On the left, we have the righting mechanism, which pivots downward to reorient a robot that is on its front face. On the right, we have the tilting mechanism, which pivots upward to lift a robot off the ground. In design of these mechanisms, a few considerations had to be made when selecting dimensions. First, the arms needed to have clearance with both the ground and wheels during normal swarm operation, and when performing 3D locomotion behaviors. In addition, the arms had to still allow for normal coupling behavior to take place. We also investigated power transmission methods for these mechanisms. We compared belts and gears, and found that although belts allowed for more optimal placement of motors to optimize center of mass, gears were able to output more torque without skipping, making them the better choice for this mechanisms. We also continued development of the PuzzleBot platform as a whole. We worked to integrate a new motor into the chassis and enabled the robot to be driven by a single motor rather than two. We also developed a new lid that wouldn't fall off when subjected to impacts from 3D locomotion behaviors. We performed characterization experiments for the mechanisms. We incrementally increased the load mass to determine the maximum load that the mechanisms could handle. We also measured power consumption of the mechanisms using a power supply, under normal operation of lifting one robot, as well as under maximum load. We also measured range of motion of these mechanisms. We found that the mechanisms were able to lift over 6 times the robot's body mass, and could last for nearly 10 hours of battery life under normal operation. We also performed experiments comparing performance between mechanisms and with a baseline no-mechanism homogeneous swarm. We used 4 main tasks. First, we measured performance on gap crossing, a task that has been analyzed with the PuzzleBots before. We also investigated obstacle descent, climbing, and lifting. For all of these experiments, we evaluated performance with regards to quantity of robots in the swarm, from a single robot up to 8 robots. We found that the 2 mechanisms performed similar at gap crossing, consistently outperforming the homogeneous swarm. In obstacle descent, we compared the righting mechanism with the homogeneous swarm and saw drastic improvements. In climbing, both mechanisms performed similarly, with the righting mechanism being able to climb up to 1 body height when 8 robots were used. Finally, for the lifting task, we evaluated the tilting mechanism's ability to lift robots of varying mass, and found that it could lift robots up to 1.8 times normal body mass, with decreasing performance as mass increased due to increased load on the coupling. These experiments show the benefits of these mechanisms and the enhanced capabilities they can add to the PuzzleBot swarm. Going forward, we plan to perform more complex swarm behaviors, including stacking PuzzleBots on top of each other, navigating outside environments like sidewalks, and climbing even taller obstacles through complex lifting behaviors. We also hope to further optimize the morphology of the mechanisms, as well as investigating other uses for the mechanisms, such as manipulation or clearing a path. Finally, we plan to integrate these into an autonomy framework, enabling 3D autonomous locomotion. This work was supported by the Robotics Institute Summer Scholars Program as well as by the Zoom Lab. We wish to thank Rachel Burson, Dr. John Dolan, and Maria Ferrato for their support of this project.